Yes, my name is Larry Hudson, the Chief Test Engineer for the Flight Loads Laboratory. I'm going to give you a brief overview of the lab and talk about some of the items that you see here on these tables. And so what we have here are these are actual shuttle tiles, and you're welcome to pass these around. And the shuttle tiles, if you know about the shuttle is an insulated structure. It has TPS on it, the shuttle tiles, and those shuttle tiles sit on an aluminum substructure. And so the shuttle tiles take all the aerodynamic heating loads, and the aluminum frame underneath that take all the aerodynamic and inertial forces. Okay, so you have a system where the heating loads do not ever get to the aluminum structure until really after it lands. And then when it lands, then the aluminum structure, because of the soak through from the tile, will heat up the aluminum structure. But as it's flying through the atmosphere, when the outer surface is hottest, the aluminum structure is not getting that hot. So when you have
this is actually
on the shuttle, you have a shuttle tile, and you have
they all have a unique number, right?
Structure,
so each one is made specifically for that spot.
Aerodynamic loads. You have hot structure materials, which is this class of material, or like the shuttle leading edge, which is made out of carbon-carbon. It can take both the aerodynamic heating loads and the aerodynamic forces and inertial forces. And so if you take a shuttle or a tile, can I see that one tile? If you take a tile, if you think of this as being the aluminum part of the space shuttle, it would be like this. You have a tile over the aluminum part. Well, in hot structure, you don't have to have that. This is what you have. This is seeing the aerodynamic heating directly, and it's strong enough at temperature to take all the aerodynamic forces. Now, what we're trying to do is integrate both these technologies into something like this, where you have a hot structure type of material that can withstand high temperatures, but you also have the insulation like a tile. So you're combining these two together. So it can take aerodynamic heating, and it also can take some loads as well. Okay, so that's sort of a next generation type of technology which we're working on right now. And just so you can touch this is a piece of carbon-carbon. This is the material that the shuttle leading edge was made out of. And this was the type of material that got damaged on that last disaster that we had. So if you wanted to just feel what that is, what that feels like. Whenever you test any of these types of structures, whether it be a high temperature material or even a room temperature structure, instrumentation is vitally important. You know, we have to understand what's happening to that structure when we're testing it, or actually when it's in flight as well. So one of the areas that we've been working on is fiber optic sensing technology. And with fiber optic sensing technology, you take an optical fiber, and in this case, the optical fiber has sensors that are embedded, that are inside of it. So it's feeling what's going on wherever it's attached to a structure. It's very similar to your nervous system, where your nerves are feeling what's happening at the various locations where you have nerves. Well, a fiber optic sensor, the way that we use it, is feeling strain at the location where it's bonded to a surface. So in this case, I don't have my computer here to show you. We're getting in the process of getting a new one, so I can't actually show you the demonstration. But here's you have a fiber optic sensor that's wrapped around this tube, and it's really like the thickness of your hair. And so if you press on the tube, you can imagine that you're feeling the strain going on there because of the pressure that you're pushing on it. Well, and there's also strain being felt other places because it's all connected. So you can see how the strain distribution changes on this as you press on it at various locations. And the way that we use the technology is that it'll feel whatever's happening on this structure, like in this case, this pressure vessel, the strain will produce an output, and it'll show up as like a deformed shape or a strain change.
So Larry, if you have a computer
here and were showing us, and they press their hand on there, you would actually see the handprint on the
Well, you
screen.
actually see, not the handprint, you see the change, you see that fiber change
The
screen.
line change.
And so
Okay.
we have, our demo looks like this helix. And so when you press on it, you see it change. But
I was just going to ask, do you have to put it in a specific shape? Because it looks like it's in a helix and it's like a specific spacing.
this was just arbitrary the way we wanted this as a demo piece. But here's an example where you can see that this fiber is on this surface. You can barely see it, but it's kind of wrapped like this. Well, it's wrapped like this, but you think about in this case there's a strain sensor at every half inch. So you almost can look at it as a grid, like little. If you just didn't look at the fiber, and look at the location of the strains, it would just be a bunch of dots in some pattern. So in this case, if you pressed on this surface, you would feel a strain distribution everywhere, because as you press on here, you might see max strain in these locations, because or even in the center, depending on where you press it. The greatest benefit that you can see from this technology is this. These are conventional wire strain gauges. These are in every airplane that you've ever flown in, there's strain gauges on them. You can see that there's a lot of weight associated with conventional strain gauges. This is about 100 strain gauges. This is about like 500 strain sensors on one fiber. And you can, it's nice. The benefit is not even worth explaining, because you can see it's just so much lighter. So eventually you'll see this technology integrated into airplanes on a routine basis. In fact, the 787 actually has fiber optic sensors on it, the Dreamliner, the Boeing Dreamliner. Okay, you can take these as well if you want. They're describing the fiber optic sensing technology that we have. And I'm going to show you one last thing. So this is what we call the large nitrogen test chamber. It's not a very creative name. It's a large chamber that we fill with nitrogen gas. Therefore, large nitrogen test chamber. And so what we test in here are those hot structure materials that are made out of materials called carbon-carbon or carbon-silicon carbide. And remember, carbon-carbon is a shuttle leading edge material. And what we try to do in here is test them to the temperatures that they would be experiencing in their actual flight environment. And the reason why we test them in this chamber, this actual door actually comes down, is because carbon-carbon or carbon burns in the presence of oxygen at about 700-ish degrees Fahrenheit. So we have to get rid of as much oxygen as we can out of this chamber when we're testing these materials, in order to maintain the integrity of the material itself, or the structure. And we typically test to about 100 parts per million of oxygen content, so very low oxygen content. In fact, the funny story that I have for this is that we accidentally shut in a moth in this building, in this chamber, and it was flying around in a circle right here. There's a front door on this big door. There's a front door that has a little window, and so we had already gone down to test condition. Not that I'm going to try to save them off, but for the sake of a test. But we were concerned about the moth. But he was flying around right here in the middle, and just when we got to just below like 19% oxygen, the moth just died. So. Felt sorry for the moth, but that proved that we didn't want to be in here when we're actually.
He gave his life for science.
Yeah, that's right. He gave his life for science. So what you see is a heating system, and you can sort of tell what we tested in here, right? The shape of it. It was like a cone. But we have two types of heating systems. We have what's called a quartz lamp heating system, which are similar to those halogen lamps that I don't know if you still have those in your home. I don't know if they still sell those anymore. But it's a lamp that you run electricity through it, and it lights up like a light bulb, and filament gets very hot, and it radiates to the surface, and it'll heat up that surface. And typically we can get those to about 2,500 degrees Fahrenheit, our surfaces. Then we have a system on the bottom called graphite heaters that get extremely hot, and you run current through those, and you just, as the more current that you run, the hotter they get. And we can heat up surfaces to about over 3,000 degrees Fahrenheit with graphite heaters. And you can see what's really required to run these heaters. You have to have water cooling and gas cooling on both systems. So it's fairly complex test to run this. A lot of different systems are operating at the same time. So you guys are welcome to come in and just kind of stare at this if you like. Please don't touch any of the heaters, the graphite heaters, with your hands, because they don't like your oil. Any questions? So we're planning on running a test in here next March or April.
Of what cameras to monitor?
Yeah, these are cameras that monitor what happens in here. Our cameras are network-based, so we can actually watch them over the internet if we wanted to.
Telework.
Actually, we ran a test here one year where we had customers that on the East Coast that they were watching a test in their home.
So what's the test you're going to do next year?
I can't tell you.
Oh.
Sorry.
Can you see if we can set a moth life?
Larry Hudson, the Chief Test Engineer for the Flight Loads Laboratory. I'm going to give you a brief overview of the lab.